At the very center of our star exists a realm that no instrument has ever directly observed, hidden beneath hundreds of thousands of kilometers of material. The temperature here reaches 15 million degrees, a heat so extreme that matter behaves in ways unfamiliar to everyday experience on Earth. The pressure crushes inward from all directions, created by the entire weight of the sun pressing down upon this hidden core continuously. This is where the journey begins for every photon that will eventually become the sunlight warming our world, many thousands of years later. Arriving at this place, even in imagination, requires adjusting to conditions that dwarf anything found elsewhere in our solar system entirely. The core extends roughly 1/4 of the way from the center to the visible surface we observe from Earth each day. This region, though representing only a small fraction of the sun's total volume, contains nearly half of the star's entire mass. The matter here is squeezed to densities far exceeding anything on our planet, reaching about 150 grams per cubic centimeter. You are listening to The Drowsy Astronaut, and tonight we are taking a slow, unhurried journey through the heart of our nearest star. This exploration will follow energy from its birth in the nuclear fires of the core to its eventual arrival on Earth as sunlight. The journey we are tracing takes approximately 100,000 years to complete, though the final sprint across space requires only 8 minutes. If you are joining us from somewhere around the world, feel free to share where you are listening from in the comments below. And if calm journeys like this help you slow down and unwind, a like or subscribe gently supports the channel and helps others find these quiet explorations. Now let us dive deeper into the core, the hidden furnace where every particle of sunlight begins its long, winding journey outward. The environment of the core is one of extremes that operate continuously, without pause, without variation, without any interruption whatsoever. For 4.5 billion years, these conditions have persisted at the heart of our sun, with remarkable stability throughout. The heat that exists here now is the same heat that warmed the Earth when life first emerged in ancient oceans. The pressure that squeezes the core today squeezed it when dinosaurs walked the planet. The heat at the center deserves particular attention, as 15 million degrees represents something far beyond any temperature we encounter on Earth directly. At this temperature, matter cannot maintain the familiar structures we know from cooler environments around us here. Atoms cannot hold their electrons in orderly orbits when the energy of motion tears them away continuously and completely. Everything at the core exists in a state called plasma, where positive nuclei and negative electrons move independently through space together. This plasma fills the core with a seething ocean of particles, moving at tremendous speeds in every direction at once. The hydrogen nuclei, which are simply single protons, travel at hundreds of kilometers per second through this environment. Constantly, they collide with one another, bounce apart, change direction, collide again in an endless dance of motion and energy. The electrons weave between them even faster, their smaller mass allowing them to achieve greater velocities under the same conditions present. The plasma glows with energy at every point, yet this glow cannot escape the core through any direct path outward. The density of the material surrounding any given point absorbs any light produced almost immediately after its creation within the plasma. A photon born at the very center might travel less than a centimeter before encountering a particle that absorbs it. The energy is not lost, but rather transferred to the absorbing particle, which will later release it as another photon traveling in a random new direction. This absorption and re-emission happens countless times. The energy passed from particle to particle like a message through a crowd. Each step carries the energy in a random direction, sometimes inward, sometimes outward, sometimes sideways through the dense material. Only the slight statistical tendency to move away from the crowded center allows any net progress toward the surface far above. This is why the journey takes 100,000 years, despite light traveling at 300,000 kilometers per second through empty space. The density of the core material contributes directly to this slow diffusion of energy from center toward the distant surface. At 150 grams per cubic centimeter, the core is denser than any substance found naturally on Earth by a significant margin. This exceeds the density of lead, exceeds the density of gold, exceeds even the density of the heaviest elements we can hold in our hands. Yet this extraordinarily dense material remains a gas in its behavior, with particles moving freely rather than locked in solid positions. The extreme temperature provides enough energy to overcome any tendency for the material to condense into even denser arrangements. The particles move too fast, carry too much kinetic energy to settle into the fixed positions that define solid matter. They ricochet off one another, maintaining their spacing through sheer energy of motion, despite the crushing pressure surrounding them. This combination of extreme density with gaseous behavior exists nowhere on Earth, only in the hearts of stars burning throughout the cosmos. Holding a cubic centimeter of core material would be impossible for many reasons beyond its temperature and radioactivity considerations. The mass of 150 grams concentrated in such a small volume would weigh noticeably in your hand if it could exist at all. But removed from the conditions that maintain it, such material would immediately expand, cool, and transform into ordinary hydrogen gas rapidly. The core state exists only because of the specific conditions present at the center of the Sun and similar stars elsewhere. The pressure creating these conditions reaches values that challenge comprehension when expressed in familiar Earth-based measurements for comparison. Approximately 265 billion times the atmospheric pressure at Earth's surface squeezes the core from all directions simultaneously inward. This pressure comes from the weight of all the overlying material, the entire mass of the Sun pressing down through gravity constantly. Every layer presses on the layers below, and at the center, this accumulated weight reaches its maximum crushing force. This immense pressure is what forces hydrogen nuclei close enough together for nuclear fusion to occur at all in the core. Protons carry positive electrical charges and naturally repel one another through electromagnetic force when they approach closely together. Under ordinary conditions, this repulsion keeps protons safely separated, unable to approach near enough for fusion to occur between them. Only the crushing pressure of a stellar core can overcome this repulsion and push protons into contact for fusion reactions. The pressure does not crush the core into ever smaller configurations because energy production creates an outward push that balances gravity. When nuclear fusion occurs, energy is released, and this energy exerts pressure on the surrounding material, pushing it outward. The hotter the core becomes, the more fusion occurs, and the more outward pressure is generated to resist further compression. This balance between gravity pulling inward and pressure pushing outward has maintained itself for billions of years of stellar operation. This equilibrium represents one of the most stable arrangements in nature, self-regulating without any external intervention required. If the core were to contract slightly under gravity's pull, the increased pressure would raise the temperature automatically in response. Higher temperature would accelerate fusion reactions, releasing more energy and pushing the core back to its original size once again. The system corrects itself, returning to balance whenever any disturbance threatens to disrupt the stable equilibrium present. The opposite adjustment works equally well. If the core were to expand slightly for any reason during its operation, expansion would reduce the pressure and temperature, slowing fusion reactions and reducing the outward push against gravity's inward pull. Gravity would then contract the core back to its equilibrium size, restoring the original conditions for stable energy production once again. This negative feedback loop makes the Sun an extraordinarily reliable energy source across astronomical timescales of billions of years duration. The stability has persisted for approximately 4.5 billion years since the Sun first ignited and began its hydrogen-burning phase. The conditions at the core today differ only slightly from conditions when the solar system was young and planets were still forming. The main change has been a gradual accumulation of helium, the product of hydrogen fusion occurring continuously at the center. This helium slowly enriches the core composition, a change that will eventually matter, but not for billions of years yet. Despite all this energy production, the core itself exists in a kind of paradoxical darkness that seems to contradict its nature. Every photon of sunlight that reaches Earth originates here, born from nuclear reactions occurring continuously at the solar center today. Yet standing within the core, if such a thing were possible, would not reveal brilliant illumination flooding the surroundings with light. The photons produced cannot travel any meaningful distance before being absorbed, making the core effectively opaque to its own radiation. The light that exists here is gamma radiation, extremely high-energy photons produced directly by fusion reactions between hydrogen nuclei. These gamma rays carry far more energy per photon than the visible light that eventually reaches Earth from the solar surface. The transformation from gamma ray to visible light occurs gradually as the energy diffuses outward through cooler, less dense material above. By the time photons escape the Sun, they have been absorbed and re-emitted so many times that their character has completely changed. The darkness of the core is not the darkness of empty space, but the darkness of perfect opacity surrounding every point. Light exists everywhere, but travels nowhere, absorbed immediately upon creation by the dense surrounding plasma filling all available space. The energy is present, but trapped, able to move only through the slow process of diffusion, from particle to particle outward. This trapped quality is what makes the journey take 100,000 years, despite the core being only about 700,000 kilometers from the surface. Scientists have never directly observed the core, and likely never will using any form of electromagnetic radiation from instruments available. The opacity extends throughout the solar interior, making it impossible for any light to reach us from below the visible surface layer. Instead, researchers study the core through helioseismology, analyzing sound waves that travel through the Sun's interior structure continuously. These waves bend and change speed depending on the conditions they encounter, revealing the hidden structure within the opaque depths. The sound waves used in helioseismology originate from convective motions near the solar surface, disturbing the underlying material rhythmically there. These disturbances travel through the Sun at speeds determined by the local temperature, density, and composition of each region traversed. By analyzing how waves propagate and where they reflect, scientists can construct detailed models of the solar interior with precision. This technique has confirmed that our understanding of core conditions matches the reality hidden from direct observation within. The boundary of the core is not a sharp edge, but a gradual transition where conditions change enough to stop nuclear reactions. Moving outward from the center, temperature and pressure both decrease as the overlying mass diminishes with increasing distance from the core. At some point, roughly 1/4 of the way to the surface, conditions drop below the threshold needed for fusion. Beyond this fuzzy boundary lies the radiative zone, where energy continues its outward journey, but no new energy is being created. The core represents the only region of the Sun where energy is actually being generated, rather than simply transported outward. Everything visible about the Sun, from its light to its warmth to its influence on planets, originates here. The surface we see when we look at the Sun is merely the place where this ancient energy finally escapes into space. The core is the true heart of the star, pumping energy outward through a vast circulatory system that spans the entire solar interior. Within this hidden furnace, the process that powers all life on Earth occurs at every moment without pause or interruption. The energy that will warm the Earth tomorrow, next year, or 100,000 years from now is being created right now continuously. The photons being born at this very moment will not complete their journey to the surface during any living human's lifetime at all. They will emerge when Earth has changed in ways we cannot predict, carrying energy from our present into an unimaginable distant future. The journey of these photons through the core is only the first step in an odyssey that will eventually bring sunlight to our world. Created in fusion reactions, immediately absorbed by surrounding plasma, re-emitted in random directions, the energy begins its slow diffusion outward. Thousands of years will pass before this energy even reaches the edge of the core itself on its wandering path. The patient process of diffusion moves energy outward at a pace that seems impossibly slow given how fast light actually travels through empty space. This contrast between light's speed and the journey's duration captures something essential about the conditions at the solar core itself. Light is not slow here, still traveling at 300,000 kilometers per second between each absorption and re-emission event occurring. The slowness comes from the random walk, the countless redirections that erase any forward progress toward the surface above. Each step might go any direction, and only the statistical tendency to drift outward allows eventual escape from the core. The core continues its work at this very moment, as it has for billions of years, as it will for billions more years yet. Fusion reactions occur, photons are born, energy begins its outward journey through the dense plasma filling the solar interior. Nothing marks this moment as different from any other in the core's long history of continuous operation throughout time. The process simply continues, steady and reliable, powering a star that powers a world that hosts the beings now contemplating it. And so we leave the core as a place, having examined its conditions, its extremes, its paradoxes, and its central role in solar operation. the energy created here must still travel outward through the radiative zone that lies beyond the core's boundary, above. This journey through the next region will occupy the photon for tens of thousands of years of continued diffusion outward. The process that began with fusion continues with transport, carrying solar energy ever closer to the surface, where escape finally becomes possible. The creation of a photon in the solar core begins with a process called nuclear fusion, where lighter atomic nuclei combined to form heavier ones. This process releases energy because the resulting nucleus has slightly less mass than the original components that created it. Combined, the lost mass is converted directly into energy, according to the relationship Einstein described in his famous equation about mass and energy equivalence. This conversion of mass to energy is what powers the sun and enables all the light and heat we receive on Earth. The specific fusion process occurring in the sun's core is called the proton-proton chain, a name describing its basic mechanism simply. Two protons, which are simply hydrogen nuclei consisting of single positive particles, must first collide and combine somehow together. This initial step is extraordinarily difficult because protons carry positive electrical charges that push them apart strongly at close distances. Only the extreme conditions at the core can force protons close enough together for the combination to occur. When two protons approach each other, their positive charges create an electrical repulsion that increases as they get closer together. Under normal circumstances, this repulsion would prevent the protons from ever touching, deflecting them away before contact could occur. The immense temperature of the core gives protons enough kinetic energy to approach very closely despite this electrical barrier pushing back. Even so, the approach is not close enough for classical physics to explain how fusion actually happens continuously. The key to understanding fusion lies in quantum mechanics, the physics of the very small that governs particle behavior fundamentally. Quantum mechanics allows particles to occasionally pass through barriers that classical physics would consider impenetrable under certain conditions. This phenomenon, called quantum tunneling, means a proton can sometimes appear on the other side of the electrical barrier unexpectedly. Without this quantum effect, the sun would not be hot enough to sustain fusion and would never have ignited. When two protons do successfully combine, they do not simply stick together in their original forms at all, actually. One of the protons quickly transforms into a neutron through a process involving the emission of other particles simultaneously. The resulting combination of one proton and one neutron forms a deuterium nucleus, a heavy form of hydrogen created in this step. This transformation releases a positron and a neutrino, particles that carry away some of the reaction's energy immediately. The positron, which is the antimatter counterpart of an electron, quickly encounters a normal electron in the surrounding plasma nearby. When matter and antimatter meet, they annihilate each other completely, converting their combined mass entirely into energy as photons created. This annihilation produces gamma-ray photons that carry the energy away from the reaction site into the surrounding plasma. These are some of the photons that will eventually become the sunlight, reaching Earth after their long interior journey. The neutrino produced in this reaction is a ghostly particle that barely interacts with matter at all under any circumstances. Unlike the photon, the neutrino can pass through the entire sun in seconds, escaping directly into space without any absorption whatsoever. Trillions of neutrinos pass through your body every second, traveling from the sun without interacting with your atoms at all. These particles carry information about the core conditions that light cannot provide due to its long imprisonment inside. The deuterium nucleus produced in the first step does not remain alone for long in the hot, dense environment of the core. It quickly encounters another proton and fuses to form helium-3, a light isotope of helium containing 2 protons and 1 neutron. This step also releases energy in the form of a gamma-ray photon added to the growing population diffusing through the core. The reaction happens quickly because deuterium is highly reactive under the conditions present at the solar center. 2 helium-3 nuclei produced by separate reaction chains must then combine to complete the proton-proton chain process entirely. When they fuse, they produce a normal helium-4 nucleus containing 2 protons and 2 neutrons in stable configuration. 2 protons are released in this final step, returning to the plasma to potentially participate in future fusion reactions later. More energy is released as gamma rays, adding to the photon population slowly diffusing through the core outward. The complete proton-proton chain converts 4 hydrogen nuclei into 1 helium nucleus, plus energy in the form of photons and neutrinos. The helium nucleus has slightly less mass than the 4 original protons, with the difference appearing as the energy released. About 0.7% of the original mass becomes energy, a tiny fraction but an enormous amount given the masses involved. The Sun converts approximately 4 million tons of mass into pure energy every single second continuously. Despite this massive conversion rate, the Sun contains so much hydrogen that it can continue for billions of years without exhausting its fuel. The core currently contains enough hydrogen to sustain fusion for roughly another 5 billion years of continuous operation at current rates. The Sun is essentially middle-aged, having burned through about half of its original core hydrogen fuel during its lifetime so far. The remaining half will last for another span similar to the entire current age of the Sun. The energy released by a single fusion reaction is tiny by everyday standards, less than would light the smallest bulb measurably. The power of the Sun comes from the astronomical number of reactions occurring simultaneously throughout the entire core volume constantly. Every second, approximately 10 to the 38th power reactions occur, a number so large it defies meaningful comprehension completely. This collective output produces the familiar sunlight that illuminates our days and warms our planet continuously. The gamma-ray photons produced by fusion carry extremely high energy, far more than visible light photons ever possess. Their wavelengths are incredibly short, millions of times shorter than the wavelengths of visible light we see around us. These high-energy photons are what begin the long journey toward the surface, though they will not remain gamma rays permanently. Over the course of their journey, they will lose energy through countless interactions, eventually becoming the gentler light we experience. The temperature required for fusion to occur sets a minimum threshold that the core must exceed to function properly. If the temperature dropped significantly below 15 million degrees, fusion would slow dramatically or stop entirely from insufficient energy. The current core temperature is actually barely sufficient for fusion, just above the threshold needed for reactions to proceed continuously. A cooler core would not sustain itself, and the Sun would begin to collapse without the outward pressure of energy production. This marginal sufficiency is actually what makes the Sun so stable and long-lived, compared to hotter burning stars elsewhere. More massive stars with hotter cores burn through their fuel far more quickly due to accelerated reaction rates at higher temperatures. The Sun's relatively modest core temperature means it proceeds at a sustainable pace for billions of years of operation. This slow burn is what allowed time for life to develop on Earth during the Sun's long, stable phase. The helium produced by fusion remains in the core, gradually accumulating as hydrogen is consumed over billions of years. The core composition has slowly changed over the Sun's lifetime, becoming more helium-rich at the very center over time. This changing composition will eventually affect how the core operates, leading to the changes that will occur in billions of years. For now, the hydrogen remains abundant enough to fuel continuous fusion without any noticeable impact on solar output. The energy created by fusion does not travel directly outward, but instead begins a random journey through the dense core material. The gamma-ray photons are immediately absorbed by the surrounding plasma, their energy briefly held by the absorbing particle. The energy is then re-emitted as new photons traveling in random directions without preference for any particular direction at all. This process of absorption and re-emission is what transforms the instant of creation into a journey lasting 100,000 years. The birth of a photon in the solar core is happening right now, at this very moment, as you listen to these words. Millions of tons of hydrogen are becoming helium, releasing energy as gamma rays that begin their long, wandering journey outward. These particular photons will not reach the surface during our lifetimes, or the lifetimes of our distant descendants either. They will emerge when the Earth has changed beyond recognition, carrying ancient energy into an unknown future ahead. The moment a gamma-ray photon is created in a fusion reaction, its journey toward the solar surface begins immediately. Moving at the speed of light, the fastest speed possible in the universe, it travels away from its birthplace incredibly quickly. Within a tiny fraction of a second, it should be able to cross enormous distances if space were empty around it. The solar core, however, is far from empty, and the photon's first journey is remarkably brief indeed. The distance a photon can travel before being absorbed is called its mean free path, a statistical measure of transparency in matter. In the solar core, this mean free path is extraordinarily short, often less than a centimeter before the next interaction occurs. The photon, traveling at 300,000 kilometers per second, covers this centimeter in an unimaginably brief instant. Then it is gone, absorbed by the plasma, its energy temporarily held by whatever particle captured it. The absorption occurs when the photon encounters an ion or electron in the dense plasma filling the core completely. The photon's energy is transferred to the absorbing particle, raising it to a higher energy state momentarily. The photon itself ceases to exist in this moment, its identity dissolved into the absorbing particle's temporary excitement. A fraction of a second later, the particle releases this energy again, creating a new photon to continue the journey. The new photon is emitted in a completely random direction, with no memory of where the original photon came from previously. It might head outward toward the surface, which would be progress in the right direction for eventual escape. It might head sideways, making no net progress toward the surface at all during this particular step. It might even head back toward the center, actually losing ground in the journey toward eventual freedom from the star. This random emission direction is the key to understanding why the journey takes so long despite light's incredible speed. If photons traveled straight outward, they would cross the sun's radius in just over 2 seconds after creation. Instead, the random walk created by countless absorption and re-emission events creates a meandering path through the interior. The net progress toward the surface is extraordinarily slow, measured not in seconds, but in millennia. The physics of random walks is well understood and can be described mathematically with reasonable precision for analysis. Each step in a random walk moves in a random direction, with no correlation between successive steps in the journey. Over many steps, there is a statistical tendency to move away from the starting point, but progress is extremely slow. The distance from the start grows only as the square root of the number of steps, not proportionally with steps. This square root relationship is what transforms a 2-second journey into one, lasting 100,000 years of wandering. If a photon takes 1 step per absorption, and each step is about a centimeter in a random direction throughout the core, after 10,000 steps, it has moved only 100 centimeters from its starting point, on average, statistically speaking. After 10 billion steps, the average distance is only 100,000 centimeters, or 1 kilometer of net progress achieved. The number of absorptions a photon experiences during its journey through the sun is almost impossible to comprehend fully. Estimates suggest something on the order of 10 to the 25th power interactions, or 10 trillion absorption events total. Each interaction takes only a tiny fraction of a second, but the sheer number of them accumulates into millennia. The journey is not slow because any single step takes long, but because so many steps are required for progress. The photon we might follow from its creation is immediately absorbed after traveling less than a centimeter outward. The particle that absorbs it holds the energy briefly, then emits a new photon in a random direction chosen by chance. This new photon is, in a sense, a continuation of the original, carrying the same energy onward through the plasma. In another sense, it is a completely new photon, with no physical continuity to the one that was absorbed. This question of identity becomes philosophical when applied to photons traveling through the solar interior on their journey. The energy is continuous, passing from photon to photon in an unbroken chain of transfers throughout. The individual photons are not continuous, each existing only briefly before being absorbed and replaced by another photon carrying forward. Whether we call this one photon's journey or a relay of energy depends on perspective and definition. The absorbing particles in the core include both ions and electrons, each interacting with photons in different ways physically. Electrons can scatter photons through a process called Compton scattering, changing the photon's direction and sometimes its energy slightly. Ions can absorb photons into their internal energy states, then re-emit them after a brief delay in the process. Both processes contribute to the random walk, though the details differ in their physical mechanisms. During the absorption and re-emission process, the photon's energy can change slightly due to various physical effects. The absorbing particle might be moving toward or away from the photon, adding or subtracting energy through Doppler effects. The re-emission might produce a photon of slightly different energy than was absorbed due to the particle's thermal motion. Over countless interactions, these small energy changes gradually reduce the photon's energy on average over time. This gradual energy loss is what transforms the original gamma ray into lower energy radiation as the journey progresses outward. Gamma rays have extremely high energy, and short wavelengths compared to other forms of light in the electromagnetic spectrum. Through millions of interactions, the energy decreases and the wavelength increases, moving through X-rays toward ultraviolet and eventually visible light. By the time the energy reaches the surface, it has become the familiar sunlight we see. The first collision after birth is just one of trillions yet to come for the energy beginning its journey. The photon absorbed in that first centimeter will be replaced by another which will travel another centimeter approximately before absorption. That photon will be replaced in turn, and so the energy continues, step by tiny step through the core. The journey has barely begun, with almost the entire sun still lying between this point and the freedom of space. The direction of each step is truly random, determined by quantum mechanical probabilities, rather than any predictable pattern for observers. There is no way to know which direction a particular photon will go when emitted after absorption occurs. Outward, inward, sideways, all directions are equally probable in the isotropic environment of the core plasma. Only statistics, applied over countless steps, creates the slow net drift toward the cooler outer regions eventually. The progress outward, when it occurs, is driven by the temperature gradient within the sun's interior regions throughout. The core is hotter than the outer regions, creating a statistical tendency for energy to flow outward over time. More photons travel from hot to cool than from cool to hot, simply because hot regions have more energy available. This asymmetry, tiny for any single step, accumulates over trillions of steps into net outward motion over millennia. The dense plasma of the core is not a peaceful environment for this slow journey through toward the surface. Particles move at hundreds of kilometers per second, colliding constantly with tremendous energy between them throughout. The photon being absorbed and re-emitted is just one small part of this seething chaos of motion and energy. The environment would instantly vaporize any material object, yet the energy passes through patiently over thousands of years. Looking at a single photon's journey gives a misleading impression of isolation in an overwhelming crowd of traveling energy. At any given moment, countless photons exist simultaneously throughout the core, all at different stages of their own journeys. The population diffuses outward collectively, with individuals making no measurable difference to the overall flow of energy. The sun does not depend on any single photon, but on the statistical behavior of unimaginably vast numbers. The first collision is followed by the second, then the third, then millions more before any significant progress has been made. The photon that will eventually become a ray of sunlight warming your face is absorbed and reborn countless times. Each rebirth sends it in a new random direction, most of which do not help its outward progress at all. The patience required for this journey is beyond any time scale meaningful to human experience completely. Beyond the core, where nuclear fusion can no longer occur due to insufficient temperature and pressure conditions, lies the radiative zone. This vast region extends from roughly 25% of the sun's radius out to about 70% of the distance to surface. The radiative zone contains most of the sun's volume, a thick shell of plasma through which energy must slowly diffuse outward. Here the photon continues its random walk, absorption and re-emission still the primary means of energy transport throughout. The conditions in the radiative zone differ from the core, with lower temperatures and densities than the central regions possess. The temperature at the inner edge is around 7 million degrees, already less than half the core's extreme conditions. At the outer edge, the temperature has dropped to approximately 2 million degrees, still unimaginably hot by Earth standards. The density also decreases throughout this region, making the plasma less opaque to radiation passing through. The decreasing density means the mean free path of photons increases as they move outward through the radiative zone. Instead of less than a centimeter between absorptions, photons might travel several centimeters before their next interaction occurs. This increased step size helps somewhat, but the total distance to be covered is enormous and still requires countless steps. The journey through the radiative zone takes the majority of the total time from core to surface, by most estimates. The energy transport in this region is called radiative diffusion, because radiation carries the energy without any bulk motion of material. The plasma itself does not move significantly, remaining relatively stable while photons pass through it continuously in all directions. The energy flows through the material rather than with it, like heat conducting through a stationary metal bar when heated. This distinguishes the radiative zone from the outer convective zone, where material motion becomes important later. The photon, continuing its journey through the radiative zone, follows the same random walk pattern established in the core. Absorbed, re-emitted in a random direction. Absorbed again, re-emitted again, countless times as it slowly diffuses outward over time. The net progress remains extremely slow, with most individual steps making no contribution to outward motion at all. Only the statistical tendency toward cooler regions creates the gradual drift that eventually moves energy toward the surface. The plasma in the radiative zone consists primarily of hydrogen and helium ions, along with free electrons throughout the volume. The composition is similar to the core, though the precise mixture varies slightly with depth and location within the zone. The hydrogen has not been processed by fusion here, remaining in its original form since the Sun was born from its nebula. This unprocessed hydrogen makes up the fuel reserve that will eventually be consumed as the core expands in the future. The temperature gradient across the radiative zone is what drives the outward flow of energy through this region continuously. Energy naturally flows from hot to cold, and the Sun maintains a temperature difference across its interior structure always. The core is hottest because fusion produces energy there, while the surface is coolest because energy escapes into space constantly. This gradient is maintained in equilibrium by the continuous energy production and loss occurring simultaneously. The journey through the radiative zone takes most of the estimated 100,000 years of total travel time. Some estimates suggest the core requires only a few thousand years to traverse, with the rest spent in this vast shell. The exact numbers depend on detailed models of solar interior conditions that cannot be directly observed from Earth. The uncertainty in total journey time ranges from about 10,000 to nearly 200,000 years, depending on assumptions. The photon, losing energy through countless interactions, continues to shift toward longer wavelengths as it travels outward. What began as gamma radiation becomes X-rays, then eventually extreme ultraviolet, as energy is shared with the plasma repeatedly. Each interaction leaves the average photon with slightly less energy than before, the difference going into the thermal motion of particles. The plasma maintains its temperature through this energy sharing, remaining hot despite the energy flowing through toward the surface. The stability of the radiative zone depends on the energy being transported efficiently enough to prevent any buildup in the regions within. If energy accumulated faster than it could be radiated away, the temperature would rise and conditions would change significantly. If energy escaped faster than it arrived from the core, the temperature would drop and the zone would contract inward. The actual state represents a balance where transport matches supply throughout the entire region continuously. No dramatic events occur during the long passage through the radiative zone for the traveling energy packet moving outward. The environment is relatively uniform, with conditions changing only gradually over vast distances of continuous plasma throughout the volume. The photon is absorbed and re-emitted in the same manner, whether near the inner edge or near the outer boundary. Tens of thousands of years pass in this steady, patient diffusion through the deep solar interior progressively. The concept of a photon taking this journey is a convenient simplification of what is actually a continuous flow of energy. Energy enters the radiative zone from the core continuously, diffuses through at all depths simultaneously, and exits at the outer edge. Individual photons exist only briefly between absorption events, with the energy being the continuous quantity throughout the process. The journey we describe is the journey of energy, personified as a photon for easier understanding. The outer edge of the radiative zone does not end abruptly at a defined boundary visible in any physical way. Instead, conditions gradually change until a different mode of energy transport becomes more efficient than radiative diffusion progressively. This transition region has characteristics of both zones, with radiation and material motion both contributing to energy flow. The shift from radiative to convective transport marks a fundamental change in how energy moves toward the surface. The vastness of the radiative zone is difficult to appreciate from descriptions of percentages and temperature gradients alone. Completely, this region extends for roughly 300,000 kilometers in thickness, more than 20 times the diameter of Earth entire. If you could travel at jet aircraft speeds through this zone, the crossing would take years of continuous flight. The photon, despite moving at light speed between absorptions, takes millennia to cross this same distance through its wandering. The patience of this journey reflects the patience of the sun itself, burning steadily for billions of years without haste. There is no urgency in the radiative zone, no deadline for energy to reach the surface by any particular time frame. The energy created today will emerge when it emerges, joining the continuous stream that has flowed for eons before it. The sun operates on timescales that dwarf human history, human civilization, and human existence entirely. The conditions that create this slow journey are essential to the sun's stable long-term energy output over time. A more transparent interior would allow energy to escape too quickly, destabilizing the nuclear reactions in the core immediately. A more opaque interior would trap energy, causing the star to expand or behave unpredictably in response. The actual opacity creates just the right flow rate to maintain the equilibrium that makes the sun reliable. This reliability is what allowed life to develop on Earth over billions of years of continuous mild illumination. The sun's output has varied only slightly over geological timescales, providing consistent energy for evolution to proceed gradually. The long photon journey is part of what creates this stability, smoothing out any variations in core output over time. What emerges from the surface is an average of 100,000 years of energy production history. The end of the radiative zone approaches as the photon continues its long random walk toward cooler regions above. The temperature continues to drop, the density continues to decrease, and eventually a threshold is reached where things change significantly. The energy that has traveled so far still has one more major transition to undergo before reaching the surface, finally. The convective zone awaits, where the method of energy transport shifts from radiation to physical motion of material upward. The estimated time for a photon to journey from the core of the Sun to its surface has captured scientific and public imagination alike. 100,000 years is the figure often cited, though estimates range from as low as 10,000 to as high as 170,000 years. This uncertainty reflects the difficulty of knowing exact conditions inside a star we can only observe from the outside currently. The physics is well understood, but the specific values of temperature, density, and composition at each depth remain somewhat uncertain. The calculation begins with the random walk model, which describes how a particle moves when each step is in a random direction. If a photon takes steps of average length L in random directions, after n steps, its average distance from the starting point is L times the square root of n. This square root relationship is what makes random walk progress so much slower than straight line travel would be. 1,000,000 steps moves you only 1,000 times L from your start. Not 1,000,000 times. The mean free path, which is the average step length, varies with depth in the solar interior due to changing conditions. In the core, where density is highest, the mean free path might be about 1 centimeter or less between absorption events. In the outer radiative zone, where density is lower, the mean free path increases to perhaps several centimeters between interactions. These values are derived from calculations of how opaque the solar plasma is at different temperatures and densities. The total number of steps required to cross the Sun from core to surface is astronomical in the most literal sense. Estimates suggest something like 10 to the 25th power individual absorption and re-emission events during the complete journey outward. This number, a 1 followed by 25 zeros, exceeds any quantity encountered in everyday experience by many orders of magnitude. Written out, it would be 10 trillion separate interactions before the energy finally escapes into space. Each interaction takes only a tiny fraction of a second, with the photon traveling at light speed between absorption events. The time spent being absorbed is also extremely brief, as excited particles quickly re-emit their captured energy as new photons. The total time, therefore, comes from multiplying incredibly brief intervals by incredibly large numbers of interactions occurring throughout the journey. The product of tiny times huge gives us the tens of thousands of years for the complete trip. To put 100,000 years in historical perspective, this is the approximate age of Homo sapiens as a distinct species on Earth. The photons warming you today began their journey when modern humans were just emerging in Africa as a population. Agriculture would not be invented for another 90,000 years after those photons were born in fusion reactions. These ancient packets of energy predate civilization, writing, cities, and all of recorded human history entirely. The last ice age reached its maximum roughly 20,000 years ago, with glaciers covering much of the northern hemisphere. The photons we receive today were already more than halfway through their journey when the ice sheets began their retreat. Human civilization has risen entirely during the time it has taken these particular photons to travel their last 50,000 years. The light from today's sunrise carries energy older than any human structure still standing on Earth. Thinking about this timescale can create a sense of connection across vast spans of time, usually beyond human perception. The warmth on your face today was created before your ancestors had developed language or culture as we know them now. Energy and matter have passed through countless forms during the photon's journey, while the photon itself remained trapped within the sun. Now free, it completes in 8 minutes a journey that began in geological deep time. The uncertainty in the exact journey time comes from imperfect knowledge of solar interior conditions at each depth precisely. Small changes in assumed temperature or density can significantly affect the calculated opacity and mean free path values used in models. Different researchers, using slightly different models, arrive at different total time estimates for the complete journey. The range from 10,000 to 170,000 years reflects these modeling uncertainties rather than any physical variation. Helioseismology provides the best constraints on solar interior conditions by studying waves that travel through the sun's interior. These acoustic waves bend and change speed depending on temperature, density, and composition at different depths within the sun. By analyzing wave patterns observed at the surface, scientists can infer interior conditions with reasonable precision throughout the interior. The results generally support the standard solar model that predicts journey times around 100,000 years. Neutrino observations provide an independent check on core conditions, since neutrinos are produced directly by fusion reactions occurring there. The rate of neutrino production depends on the fusion rate, which in turn depends on core temperature and density precisely. Measured neutrino rates match predictions from the standard model reasonably well after initial discrepancies were explained by neutrino physics. This agreement supports the same interior models used to calculate photon journey times for energy escaping. The journey time has practical implications for our understanding of solar variability and its effects on Earth's climate. Variations in solar output that affect Earth's climate are smoothed by the 100,000-year journey, averaging out short-term changes. Only sustained changes in core fusion lasting many millennia would appear at the surface as significant output variations eventually. This smoothing provides one source of the sun's remarkable stability, as observed over human timescales of measurement. If the sun's core suddenly changed its energy output dramatically today, we would not notice any difference in sunlight for millennia. The photons currently reaching us were created long ago, and the reservoir of energy diffusing through the interior would buffer any changes. Only after the pipeline of energy had adjusted would the new output rate appear at the surface and affect Earth. This lag provides a sort of inertia to solar behavior that helps maintain climate stability on shorter timescales. The photon that began its journey before modern humans existed has now nearly completed its traverse of the radiative zone. It approaches the boundary where energy transport shifts from radiation to convection, a transition that will dramatically speed its progress. The remaining journey to the surface, though still complex, will take only a tiny fraction of the time already spent. Freedom approaches for energy that has been trapped within the sun since before human history began. The timescale also means that the sun we see is not the sun as it currently exists in any instantaneous sense. The surface we observe shows conditions from about 8 minutes ago, with light taking that time to reach us from there. The energy powering that surface emerged from a core that existed 100,000 years ago, reflecting ancient conditions at that time. We observe a composite of different eras, a snapshot from minutes ago powered by energy from millennia past combined together. This layering of time in what seems like a simple observation of sunlight reveals the complexity hidden in everyday experiences. The warmth, light, and life-giving energy we receive has a history extending back before human consciousness existed on Earth. Each sunrise brings ancient energy to a new day, connecting the present moment to the deep past through unbroken chains. The photon's journey is complete, but its energy continues to participate in the ongoing processes of the Earth below. At approximately 70% of the distance from the Sun's center to its surface, the character of energy transport changes fundamentally. The temperature here has dropped to about 2 million degrees, still tremendously hot, but cool enough for an important transition. The radiative diffusion that carried energy through the deeper interior becomes less efficient than an alternative method available. This boundary region, called the tachocline, marks the shift from radiative to convective energy transport toward the surface. Convection is the bulk movement of material, with hot fluid rising and cool fluid sinking in continuous circulating patterns. In a pot of boiling water, convection creates the roiling motion visible at the surface as hot water rises and releases heat. The same basic physics operates in the sun's outer layers, but on a vastly larger scale than any kitchen example. Giant cells of plasma rise toward the surface, release their energy, and sink again in patterns repeating continuously. The transition to convection occurs because the plasma at these depths becomes more opaque to radiation than at greater depths. This increased opacity makes radiative diffusion less efficient at carrying energy outward through the material in this region. At the same time, the lower overall density makes it easier for hot material to rise through its surroundings. The combination makes convection more efficient than radiation for energy transport in the outer third of the sun. The tachocline itself is a thin layer of particular interest because of its role in the sun's magnetic field generation. The radiative zone below rotates roughly as a solid body, with the entire interior turning together at the same rate. The convective zone above rotates differentially, with the equator spinning faster than the polar regions in measurable ways. The tachocline is where this differential rotation begins, creating shearing motions that generate magnetic fields through dynamo effects. The photon's journey changes character when it enters the convective zone after crossing the tachocline boundary above it. Rather than diffusing slowly through stationary material, the energy is now caught up in rising currents of plasma. The hot plasma carries the energy with it as it ascends, moving much faster than radiative diffusion could transport it. The journey that took tens of thousands of years through the radiative zone will take only weeks or months through the convective region. The size of convective regions' cells varies with depth in the convective zone, with larger cells in the deeper regions below. Near the tachocline, convection cells might span tens of thousands of kilometers, carrying enormous amounts of material in their flow. Higher up, the cells become smaller, until at the surface they appear as granules only about 1,000 kilometers across. This hierarchy of cell sizes creates complex flow patterns throughout the entire convective zone continuously. The plasma rising in convection currents carries energy as heat stored in the motion of particles within the rising material. As the plasma rises, it expands due to decreasing pressure at higher altitudes in the solar atmosphere above. This expansion cools the plasma, reducing its energy content through the work done against the surrounding environment during the rise. The energy lost through cooling is what gets transported outward, radiated away as the plasma approaches the surface. The energy the photon carries is now part of a rising plume of hot plasma, moving toward the surface relatively quickly. The plasma might rise at speeds of several kilometers per second, covering vast distances in hours rather than millennia of waiting. The photon is still absorbed and re-emitted within the rising plasma, but now both photon and plasma move outward together. The random walk continues, but in a reference frame that is itself moving toward the destination now. The convective zone extends for approximately 200,000 kilometers from the tachocline to the visible surface above. This distance, though substantial, is crossed much more quickly than the radiative zone due to the bulk motion of material. Estimates suggest the convective crossing takes only a few weeks or months, compared to the tens of thousands of years below. The final approach to freedom is dramatically faster than the long imprisonment that preceded it. The structure of convection in the Sun has been studied through both observation and computer simulation extensively over decades. The surface granulation is directly visible, showing the tops of the smallest convection cells as they release heat into space. Larger scale flows called supergranulation appear in careful observations of surface motions and patterns in solar plasma. The deepest convection currents are inferred from helioseismic observations and theoretical models of solar interior dynamics. The rising and sinking motions in the convective zone are not smooth and steady, but turbulent and chaotic in their behavior. Plumes of hot material rise in complex patterns, interacting with descending cool material in constantly changing configurations continuously. The flow is three-dimensional and time-varying, impossible to predict in detail even with the best computer simulations available. This turbulence is what generates the complex magnetic behavior seen at the solar surface regularly. The temperature continues to drop as the photon approaches the surface, carried by rising convective currents upward. From 2 million degrees at the tachocline, it decreases to about 5,500 degrees at the visible surface. This temperature determines the color of the light that will eventually escape, the yellow-white that characterizes our Sun. The photon's energy, reduced through countless interactions, is now appropriate for visible light wavelengths. The final stages of the journey bring the energy through ever smaller convection cells as the surface approaches closely. The cells here last only 10 to 20 minutes, before being replaced by new patterns of rising and sinking material. The surface is constantly renewed by convection from below, with hot material appearing, cooling, and sinking in endless cycles. The photon is carried on these currents, approaching the moment of escape with every rising plume. The density of the plasma continues to decrease as the surface approaches, making the material more transparent to radiation. Eventually, the density becomes low enough that photons can travel significant distances without being absorbed at all. This transition from opaque to transparent defines the visible surface of the Sun, the photosphere, where photons finally escape. The exact location of this transition determines where sunlight is born from the observer's perspective. The approach to the photosphere marks the end of the photon's long imprisonment within the solar interior below. After 100,000 years of random walking, absorption and re-emission, slow diffusion and convective transport, freedom finally approaches. The energy created when modern humans were just evolving is about to escape into space as visible light energy. The journey that began in the nuclear fires of the core is nearly complete at last. The photosphere is not a solid surface, but a region where the sun transitions from opaque to transparent to outgoing radiation. This layer is only about 500 kilometers thick, a remarkably thin shell compared to the sun's total radius of nearly 700,000 kilometers. Within this narrow region, photons make their final escape, transitioning from trapped to free in the span of a few hundred kilometers only. The visible surface we see when we look at the sun is this photosphere, the deepest layer from which light can reach us. The temperature at the photosphere is approximately 5,778 Kelvin, or about 5,500 degrees Celsius in more familiar units. This temperature, while still extremely hot by earthly standards, is much cooler than the core where the photon's journey began originally. The temperature determines the color of the emitted light, with this value producing the yellow-white characteristic of sunlight we observe. A hotter photosphere would appear more blue, while a cooler one would look more red to observers. The granulation visible on the solar surface represents the tops of convection cells rising from the depths of the convective zone. Each granule is a column of hot plasma that has risen to the surface and is now releasing its energy into space. The bright centers of granules are where the hot material surfaces, while the darker edges are where cooled material sinks back down. This pattern covers the entire visible disk of the sun, constantly shifting as new cells replace old ones. A typical granule spans about 1,000 kilometers across, roughly the size of a large Earth country like France or Texas. Each granule exists for only about 10 to 20 minutes before being replaced by a different configuration of rising and sinking material. The surface is constantly renewing itself through this convective process, with no permanent features in the granulation pattern persisting. Looking at the sun's surface is like watching a pot of boiling water, but on a scale that dwarfs earthly comparisons. The photon approaching the photosphere has been through countless transformations since its birth as a gamma ray in the core. Its energy has decreased through millions of interactions, shifting from gamma ray to X-ray to ultraviolet and now to visible wavelengths. The photon we are following might now be yellow or orange or red, depending on exactly how much energy it has lost. It is about to complete a journey that has taken 100,000 years, from origin to escape finally. As the photon reaches the photosphere, the plasma around it becomes increasingly transparent to its passage outward towards space. Fewer and fewer particles are available to absorb and re-emit the photon, allowing it to travel farther between interactions. Eventually, the photon finds itself able to travel without encountering any absorbing particle at all during its path. This moment marks the true escape, when the photon breaks free from the sun's gravitational embrace of opacity. The escape is not dramatic in any physical sense, just a photon that happens not to be absorbed before leaving the solar atmosphere. No barrier is crossed, no membrane is penetrated, No event marks the transition from trapped to free beyond the simple absence of absorption. The photon simply travels outward and keeps traveling. Nothing stopping it, nothing redirecting it, nothing absorbing it anymore. After 100,000 years of imprisonment, freedom comes quietly and without ceremony. The moment of escape is instantaneous, in the sense that the photon travels at light speed without interruption from this point forward. From the photosphere, it will take about 8 minutes to reach Earth, a mere instant compared to the journey already completed behind. The photon will pass through the corona, the Sun's outer atmosphere, without significant interaction due to the low density. It will cross the gulf of space between Sun and Earth, encountering almost nothing along the way. Looking back at the Sun from the photon's new vantage would reveal the photosphere as a glowing sphere of yellow-white light behind. The granulation pattern would be visible, the dark spots of sunspots where magnetic fields suppress convection, locally appearing as blemishes. The corona would extend outward as a pearly halo, visible during eclipses but normally hidden by the photosphere's brilliance and glare. The photon sees none of this, of course having no experience or perception of its journey at all. The photosphere emits light across a continuous spectrum of wavelengths, from infrared through visible to ultraviolet in a smooth distribution. This distribution follows a pattern called blackbody radiation, characteristic of hot objects at thermal equilibrium emitting energy continuously. The peak of the Sun's emission falls in the visible range, which is why our eyes evolved to be most sensitive to these wavelengths. The sunlight we see is the sunlight the Sun produces most abundantly at its surface temperature. The photons escaping from the photosphere stream outward in all directions, not just toward Earth, which is a tiny target. The Sun radiates its energy spherically, with only a tiny fraction of the total output intercepted by our small planet. For every photon that reaches Earth, billions of others travel into empty space, never encountering anything at all during their journey. The solar system is mostly empty, and most photons will travel forever without being absorbed by anything. The total energy released from the photosphere every second is enormous, approximately 3.8 times 10 to the 26th watts. This is the luminosity of the Sun, the rate at which it converts its mass into energy that escapes as radiation into space. The number is so large that comparisons to human power consumption are almost meaningless for understanding practically. The Sun produces more energy every second than human civilization could use in millions of years of current consumption. The photosphere is the visible face of the Sun, but not the true outer edge of the solar atmosphere extending beyond. Above the photosphere lies the chromosphere, a hotter layer visible during eclipses as a thin red ring around the obscured disk. Above that is the transition region, and above that the corona, extending millions of kilometers into space outward. These outer layers are so tenuous that photons pass through them without significant absorption during their escape. The photon has now left the Sun entirely, traveling at 300,000 kilometers per second towards its unknown destination ahead. It joins the river of photons flowing continuously from the solar surface, an unending stream of ancient energy escaping into the universe. The journey through the Sun is complete, but the journey through space is just beginning as it heads outward. For photons lucky enough to travel toward Earth, about 8 minutes of travel time remain before arrival occurs. The escape from the photosphere represents a transition from chaos to simplicity, for the traveling energy packet now free. Inside the sun, the photon was constantly buffeted, absorbed, re-emitted, redirected, slowed in its net progress tremendously over millennia. Outside, in the near vacuum of space, the photon travels in a straight line without any interference at all. The contrast between the interior journey and the exterior journey could not be more extreme in character. The photon carries no record of its long imprisonment, no memory of the trillions of absorptions that delayed its escape so significantly. It is simply a packet of electromagnetic energy, traveling at light speed, indistinguishable from a photon just created by any physical test. The history we have traced exists only in our understanding, not in the photon itself, which has no internal properties, carrying historical information. The journey is complete, the energy is free, and the sunlight that will warm Earth travels now through empty space toward us. The distance from the Sun to the Earth is approximately 150 million kilometers, a span of space called the astronomical unit. Light travels at about 300,000 kilometers per second in the vacuum of space, without impediment. Simple division reveals that the crossing takes approximately 500 seconds, or about 8 minutes and 20 seconds total. After 100,000 years inside the Sun, the final sprint to Earth takes less than 10 minutes. The contrast between these two timescales is among the most striking facts about the photon's complete journey from core to planet. Inside the Sun, the photon traveled at light speed between absorptions, but made almost no net progress over millennia of wandering. Outside, that same light speed carries the photon across 150 million kilometers in about 8 minutes flat. The difference is entirely due to the presence or absence of matter to impede the photon's straight-line progress. The space between the Sun and Earth is not perfectly empty, but it is so close to a vacuum that photons travel unimpeded. The solar wind fills this space with charged particles streaming outward from the Sun at hundreds of kilometers per second. These particles are far too sparse to significantly interact with photons, numbering only a few per cubic centimeter on average. The photon passes through this tenuous medium as if it were not there, the space effectively empty. The solar wind particles that share the journey with our photon travel much more slowly than light does through space. Charged particles ejected from the Sun take several days to reach Earth, not 8 minutes like photons do. This difference becomes important during solar storms when enhanced particle flows can disrupt satellites and power grids on Earth. The photons arrive first, providing about a day's warning before the particles arrive with their disruptive potential. As the photon crosses the inner solar system, it passes the orbits of Mercury and Venus on its way to Earth. Mercury orbits at about 40% of Earth's distance from the Sun, receiving far more intense radiation. Venus orbits at about 70% of Earth's distance, still receiving nearly twice the solar energy we do. Neither planet intercepts our particular photon, which continues its straight-line journey toward Earth's location specifically. The Earth appears as a tiny target in the vast sphere of space surrounding the Sun. At our orbital distance, the Sun emits photons in all directions equally, with only a tiny fraction aimed at the small solid angle Earth occupies. Calculations show that about 1/2 billionth of the Sun's output is intercepted by our planet's disk. During any moment, most photons leaving the Sun will travel through empty space forever, never encountering any surface to absorb them. The photon we are following happens to be among the lucky fraction heading directly toward Earth at this moment. Its path was determined by the random direction of its last emission from the photosphere. Pure chance aiming it at our planet. Trillions of other photons left the photosphere at the same moment, heading in other directions through the solar system. They will pass through empty space, some perhaps encountering other planets or moons, most meeting nothing at all. The void between planets is remarkable in its emptiness when examined closely at small scales between the worlds. If you could somehow hover in space between Earth and the Sun, you would see almost nothing around you. The particles of the solar wind would be invisible, their density far too low to perceive even collectively over volumes. Only the Sun behind and the Earth ahead would be visible. Two islands of matter in an ocean of nearly perfect vacuum. The journey across this void takes the photon past no landmarks, through no features, across no boundaries of any note. Space here is simply empty, with nothing to mark the progress of the photon toward its destination ahead of it. The photon does not experience this journey in any meaningful sense, having no consciousness or perception at all. It is simply electromagnetic energy propagating through vacuum, physics happening without any experiential quality involved. The approach to Earth begins when the photon is close enough for the planet to appear as more than a point of light. At about 1 million kilometers out, Earth would appear as a small disk showing phases like the Moon does from Earth. The blue oceans, white clouds, and brown-green continents would begin to be distinguishable if the photon could see them. Of course, the photon sees nothing, simply traveling in a straight line determined by its departure from the Sun. The final approach brings the photon into the region of space dominated by Earth's gravitational and magnetic environment. The photon itself is unaffected by Earth's gravity in any practical sense during its passage to our atmosphere. The path is so short, at light speed, that gravitational bending is utterly negligible for the photon's trajectory. Arriving here, the photon continues straight toward the point on Earth that lies along its path from the Sun. The first substantial matter the photon encounters since leaving the Sun is Earth's atmosphere, reaching up into space. The atmosphere extends hundreds of kilometers above the surface, though most of its mass is concentrated in the lowest layers. The exact point where space ends and atmosphere begins is not sharply defined, but is conventionally set at 100 kilometers. The photon crosses this arbitrary boundary without any change in its behavior, continuing downward toward denser air. The upper atmosphere is thin enough that most photons pass through without interaction during their initial entry. As the photon descends, the air becomes denser and the probability of interaction increases with each meter traversed. The specific fate of our photon depends on its wavelength and the molecules it encounters on its path downward. Some photons will be absorbed, others scattered, and others will pass through to reach the surface below. The 8-minute journey from Sun to Earth is complete when the photon first encounters the atoms and molecules of our air. The total journey, from creation in the solar core to arrival at Earth, has taken approximately 100,000 years and 8 minutes. The overwhelming majority of this time was spent inside the Sun, with the crossing of space a mere afterthought. The photon that began its existence before human civilization now arrives at a world transformed beyond recognition. The energy carried by this photon will now participate in Earth's systems in ways that connect the solar core to our daily experience of warmth and light. Directly, the surface of Earth receives this energy continuously, photons arriving by the trillions every second from the solar photosphere. Each photon carries a small packet of energy that originated in nuclear fusion reactions occurring 100,000 years ago approximately. The warmth of sunshine on skin, the brightness of daylight, the growth of plants, all derive from this ancient energy arriving. The sun's output powers nearly everything that happens on Earth's surface through this continuous delivery of photons. The photon approaching Earth right now is one among countless others, making the same journey simultaneously from the Sun. The solar luminosity represents about 384 septillion watts of power, radiating outward in all directions continuously. Earth intercepts about 170 petawatts of this output. Still an almost incomprehensible amount of energy arriving constantly. This river of photons has flowed continuously for 4.5 billion years, powering life on Earth throughout. The journey from core to Earth spans scales that challenge human comprehension when considered fully and carefully. The core, where fusion occurs, is 15 million degrees, while Earth's surface averages about 15 degrees Celsius by comparison. The density changes from 150 grams per cubic centimeter to the near vacuum of space to our thin atmosphere. The timescale shifts from 100,000 years of diffusion to 8 minutes of free flight. The photon carries no awareness of these contrasts, having no capacity for experience or comparison of any kind. It is simply energy propagating according to the laws of physics that govern all electromagnetic radiation universally. The meaning we find in this journey is our own construction, an understanding that physics itself does not share. Yet this understanding connects us to processes occurring inside our star, making the distant and ancient somehow immediate and present. The final moments of the photon's journey bring it into contact with the atmosphere that protects and sustains life on Earth. What happens next depends on many factors, including the photon's wavelength, its angle of entry, and simple chance. Some photons will reach the surface intact. Others will be absorbed or scattered by atmospheric molecules along the way. Each outcome represents a different way for the photon's energy to participate in Earth's complex energy systems ongoing. The atmosphere acts as a filter, selecting which photons reach the surface and which are absorbed or redirected along the way. Ultraviolet photons are largely absorbed by ozone in the upper atmosphere, protecting life from their harmful effects below. Visible light photons mostly pass through, giving us the daylight that illuminates our world during daytime hours. Infrared photons have varied fates, some absorbed by water vapor and carbon dioxide, others reaching the ground directly. The photon we have followed completes its journey in one of countless possible ways, depending on circumstance and chance. Perhaps it is absorbed by a molecule of nitrogen high in the atmosphere, its energy converted to molecular motion immediately. Perhaps it is scattered by oxygen molecules, bouncing off in a new direction that gives the sky its blue color. Perhaps it continues straight through, reaching the surface to warm rock or water, or skin below directly. Whatever its specific fate, the photon's energy becomes part of Earth's energy budget from this moment forward, continuously. The energy that was born in nuclear fusion, that spent 100,000 years diffusing through the solar interior patiently, that crossed space in 8 minutes freely now participates in the processes that make Earth a living world uniquely. The journey is complete, but the energy continues in new forms, transformed but never destroyed according to fundamental physics. The moment a photon from space first touches Earth's atmosphere marks the beginning of its final transformation into something new. The thin upper atmosphere extends hundreds of kilometers above the solid surface, a gradual transition from space to air below. Molecules of nitrogen and oxygen become increasingly common as altitude decreases toward the ground progressively. The photon that traveled unimpeded for 150 million kilometers now encounters matter once again after 8 minutes. The interaction between photons and atmospheric molecules creates the familiar appearance of our sky during daylight hours. Blue light scatters more readily than red light when it encounters the small molecules of nitrogen and oxygen present. This preferential scattering sends blue photons bouncing in all directions, filling the sky with scattered blue light visible everywhere. The sun itself appears yellow because some of the blue light has been removed from the direct beam by this scattering. A photon that is scattered does not disappear, but simply changes direction while maintaining its energy and wavelength approximately. The scattered photon may bounce multiple times before reaching the surface or escaping back to space above. This is why the entire sky appears bright during the day, rather than just the direction of the sun itself. The light reaching us from the blue sky consists of scattered solar photons that have bounced off atmospheric molecules overhead. The sky near the horizon appears paler and sometimes reddish because of the longer atmospheric path involved there. Photons reaching us from the horizon have traveled through more atmosphere than those from directly overhead significantly. More scattering occurs along this longer path, removing more blue light and leaving more red and orange remaining. Sunrise and sunset display vivid colors for this same reason, the low sun angle creating very long atmospheric paths. Clouds add another layer of complexity to the photon's potential fates as it descends through the atmosphere now. Water droplets and ice crystals in clouds scatter light very effectively across all wavelengths without color preference operating. This non-selective scattering is why clouds appear white or gray rather than blue like the clear sky does. A photon encountering a cloud may be scattered many times before emerging, sometimes reflected back to space entirely. The fraction of sunlight reflected by clouds, ice, and bright surfaces is called Earth's albedo, measuring overall reflectivity. About 30% of incoming solar energy is reflected back to space without being absorbed by anything present. This reflected light carries its energy back into the void, never participating in Earth's energy systems at all. The remaining 70% is absorbed somewhere, by atmosphere, ocean, land, or living things on the surface below. Photons that pass through the atmosphere without being scattered or absorbed reach Earth's surface directly. As we observe, the direct beam of sunlight feels warm because these photons carry substantial energy in concentrated form from above. When they are absorbed by surfaces like skin, rock, water, or plants, their energy becomes heat or chemical potential energy. This is the moment when solar energy truly arrives on Earth and begins powering terrestrial processes. The absorption of a photon is the end of that particular photon's existence as a discrete entity traveling freely. The energy that was a photon becomes something else entirely. Molecular vibration, chemical bond energy, electrical signals in eyes detecting light. The photon does not continue after absorption, but rather transforms completely into other forms of energy storage. Yet the energy itself is conserved, merely changing form rather than disappearing from the universe entirely. Surfaces that appear colored to us are selectively absorbing some wavelengths, while reflecting others back toward observers. A red apple absorbs blue and green photons, while reflecting red ones toward our eyes to be detected. A green leaf absorbs red and blue photons for photosynthesis, while reflecting green ones that we perceive looking at it. The colors we see in the world are created by patterns of selective absorption and reflection occurring constantly. The photon that has traveled from the solar core may end its journey in countless different ways on Earth. It might warm a rock on a mountainside, adding a tiny amount to the rock's thermal energy content immediately. It might be absorbed by the ocean, warming seawater that will later evaporate and form clouds overhead eventually. It might trigger a chemical reaction in a leaf, its energy captured in a sugar molecule for later use. One of the most significant fates for a solar photon is absorption by the chlorophyll molecules in plant leaves worldwide. Chlorophyll absorbs red and blue light strongly, using this energy to power the reactions of photosynthesis continuously operating. The photon's energy, born in nuclear fusion, becomes the chemical energy stored in sugar molecules through this process. This stored energy then powers the entire food web of life on Earth as organisms eat plants or each other. Every calorie of food we eat ultimately traces back to photons that were captured by photosynthesis at some point. The bread we eat contains energy from wheat that absorbed sunlight in a field during its growing season. The meat we eat comes from animals that ate plants that absorbed sunlight to grow as living organisms. The photon's journey from solar core through radiative zone to photosphere to space to Earth to leaf ends in our bodies. The human eye is another remarkable destination for photons, completing their 100,000-year journey from creation. Specialized cells in the retina contain molecules that change shape when they absorb photons of visible light wavelengths. This shape change triggers nerve signals that travel to the brain, creating the experience of vision for us. The photon that spent millennia diffusing through the sun now, in an instant, becomes a moment of seeing. The photons we see by have already completed their journey before we perceive them with our visual systems. The light entering your eye right now left the sun's surface about 8 minutes ago during its transit here. The photons that became this light left the sun's core roughly 100,000 years before that departure. Every moment of vision connects us to the deep past of our star through this chain of energy transfer. When the sun sets below the horizon, the photons that would reach your location now travel past Earth into space. The darkening sky represents the absence of scattered photons reaching your eyes during nighttime hours. Yet photons continue to leave the sun at the same rate, reaching the day side of Earth continuously without pause. The rotation of Earth, not any change in the sun, creates our experience of day and night alternating. At night, other photons from distant stars complete their own journeys to reach our eyes across vast distances. These photons left their stars' surfaces years, centuries, or millennia ago, depending on the star's distance from Earth. Like solar photons, they were born in stellar cores and spent long periods diffusing outward before escaping into space. The night sky is filled with ancient light, each star sending photons that began their journeys long ago. The photon that reaches Earth becomes part of a complex energy system that sustains all life on our planet. Solar energy drives the water cycle, evaporating water that later falls as rain to nourish ecosystems everywhere living. Solar energy creates temperature differences that drive winds and ocean currents around the globe, continuously moving. Solar energy powers photosynthesis, which produces oxygen and food for nearly all organisms on Earth's surface. The 100,000-year journey of a single photon is one thread in the tapestry of energy flow that sustains our world. Trillions of photons make this journey every second. A continuous river of energy connecting sun to Earth without interruption. The warmth we feel in sunshine, the growth we see in gardens, the sight that fills our eyes, all derive from this flow. The ancient light reaches us constantly, a gift from nuclear fires burning at the heart of our star. Our sun is one star among hundreds of billions in the Milky Way galaxy, each processing energy in similar ways fundamentally. The physics of stellar interiors applies across all these stars, with fusion producing energy that must diffuse outward somehow. Photons in distant suns make journeys similar to what we have traced, though the details vary with stellar properties. The process we have followed in our sun occurs throughout the universe wherever stars burn hydrogen into helium. Stars differ in their masses, which determines almost everything else about their structure and behavior over time. More massive stars are hotter, denser in their cores, and burn through their hydrogen fuel much faster than smaller ones. Less massive stars are cooler, less dense, and can burn for trillions of years due to their slower consumption rates. Our sun falls in the middle range, a yellow dwarf star with a lifespan of about 10 billion years total. Red dwarf stars are the most common type of star in the universe, far outnumbering stars like our sun. These small, cool stars have masses ranging from about 8% to about 50% of the sun's mass typically. Their low mass means lower core temperatures and slower fusion rates, producing far less light than our sun does. A red dwarf might shine for 1 trillion years, far longer than the current age of the entire universe. The internal structure of red dwarf stars differs significantly from what we have described for our sun here. In the smallest red dwarfs, the entire star is convective, with no radiative zone separating core from surface layers. Hot plasma rises from the core to the surface, releases its energy, and sinks back down to be reheated continuously. This means photons in the smallest red dwarfs may have shorter journeys than in stars like our sun. In a fully convective star, energy is carried outward by moving plasma rather than by photons diffusing through stationary material. The convection process is much faster than radiative diffusion, taking perhaps millions of years rather than 100,000. Of course, the core still produces energy through fusion, and photons still carry that energy through the plasma itself. But the bulk motion of material dominates the energy transport, changing the nature of the journey significantly. Larger stars than our sun have different structures as well, with proportionally larger radiative zones typically present. A star twice the sun's mass would have a larger, hotter core, producing energy at a faster rate. Continuously, the radiative zone would extend through a larger fraction of the star's radius, in such cases typically. Photon journey times in such stars might be longer or shorter, depending on the competing effects of size and density. The very largest stars, blue giants with masses 10 or 20 times the Sun's mass, are extreme in many ways. Their cores are so hot and dense that fusion proceeds at tremendous rates, producing enormous energy outputs constantly. These stars live fast and die young, exhausting their hydrogen in just a few million years of burning. The photon journey in such stars might take tens of thousands of years, despite their greater size overall. Blue giant stars also develop different fusion processes than the proton-proton chain that dominates in our Sun. At higher temperatures, a process called the CNO cycle becomes the primary way hydrogen fuses into helium effectively. This cycle uses carbon, nitrogen, and oxygen as catalysts, achieving the same end result by a different pathway. The energy produced takes the same form, gamma-ray photons, that must diffuse outward through the dense stellar interior. Giant stars that have exhausted their core hydrogen develop complex layered structures as they age further along. These stars may have multiple zones where different fusion processes occur at different depths inside the star. Energy transport becomes complicated, with radiation dominating some regions and convection dominating others throughout the structure. The journey of a photon through such a star would be even more complex than what we traced. Every point of light in the night sky represents photons that have completed their own internal stellar journeys. The light from Sirius, the brightest star in our sky, left that star's surface about 8 years ago. But those photons were born in Sirius's core long before that, spending their own millennia diffusing outward through plasma. The starlight we see has ancient origins inside distant stellar cores throughout the galaxy. The nearest star system to our Sun is Alpha Centauri, a triple star system about 4 light-years away from us. Light from Alpha Centauri A, the primary star, takes about 4 years and 4 months to reach us here. Photons leaving that star's core right now will not emerge from its surface for perhaps 100,000 years or more. Then they will spend another 4 years crossing the space between that star and ours. The combined journey for a photon from Alpha Centauri's core to our eyes would span over 100,000 years. Most of that time is spent inside the star, just as with our Sun, with interstellar travel taking only years. The photons we see from Alpha Centauri tonight began their existence before modern humans developed writing or agriculture. Ancient light from ancient fusion reaches across space to shine in our sky. More distant stars have correspondingly longer journeys for their photons to complete before reaching our eyes here. The star Betelgeuse, in the constellation Orion, is about 700 light-years from Earth at present. Photons leaving Betelgeuse now will reach Earth 700 years from now, in a future we cannot imagine clearly. Those photons are being born in Betelgeuse's core right now, beginning journeys that will span 700 millennia. The farthest stars visible to the naked eye are thousands of light-years away from our position in the galaxy. Their light has traveled for millennia to reach us, and their photons were born in stellar cores hundreds of millennia before departure. Looking at the night sky is looking into the deep past, seeing stars as they were long ago. The photons completing their journeys tonight carry information about ancient stellar conditions. Galaxies beyond our own contain trillions of stars, each producing photons through the same basic processes we traced. The Andromeda Galaxy, visible to the naked eye on dark nights, is about 2.5 million light-years away. Its photons have traveled for 2.5 million years to reach us, and they were born even longer ago. The light we see from Andromeda departed when early human ancestors first began walking upright in Africa. The universe is filled with photons making their long journeys from stellar cores to whatever destinations await them. Most will travel forever through expanding space, never encountering anything to absorb their energy at all. A fortunate few will warm planets, trigger photosynthesis, or enter the eyes of beings capable of wondering about their origin. The process that seems remarkable when we focus on our sun is utterly ordinary when viewed on cosmic scales. The physics governing photon journeys is the same throughout the universe, applying equally everywhere. Stars burn continuously, gravity compresses stellar cores, fusion releases energy, photons diffuse outward through plasma, and eventually they escape into space. This sequence occurs in galaxies billions of light-years away, exactly as it does in our own sun nearby. The universe operates according to consistent laws that we can understand from our tiny vantage point. This universality is part of what makes physics so powerful as a way of understanding the cosmos around us. By studying our sun, we learn principles that apply to every star that has ever existed anywhere in the universe. The photon journey we traced in detail describes, in essence, what happens in every star everywhere, continuously. Local knowledge becomes universal knowledge through the consistency of physical law throughout the cosmos. At this very moment, deep within the sun's core, new photons are being born from the fusion of hydrogen nuclei. The process that created the photons now warming Earth continues without pause or interruption inside our star today. Fusion reactions occur trillions of times each second, each one releasing a tiny packet of energy into the plasma surrounding it. The sun is a continuous engine, not a stored supply of energy being depleted like a battery draining. The photons being created right now will not reach the sun's surface for roughly 100,000 years of diffusion. They will wander through the radiative zone, absorbed and re-emitted countless times, making slow net progress outward gradually. The sunlight that will warm Earth in the year 100,000 does not yet exist as sunlight today. It is still gamma radiation deep within the solar interior, beginning its long, patient journey toward escape. This perspective reveals the sun as a system operating on timescales utterly different from human experience normally. The light we see today was created before humans developed agriculture, before cities were built, before writing existed anywhere. The light that will shine on future generations is being created now, to emerge after time spans we can barely comprehend. The sun connects past and future through the slow, patient diffusion of energy from core to surface. The core contains enough hydrogen to continue fusion for approximately another 5 billion years of stellar lifetime. This represents a stable energy source on timescales that dwarf anything in human experience or planning considerations. Civilizations will rise and fall. Species will evolve and go extinct. Continents will drift and reshape themselves completely. Through all of this, the sun will continue creating photons at nearly the same rate, powering whatever life exists. The rate of fusion in the sun's core has been remarkably constant for billions of years of stellar history already. Small variations occur due to subtle changes in core composition, as hydrogen slowly converts to helium over time. But these changes are gradual, occurring over hundreds of millions of years, imperceptible on human timescales entirely. The sun we see today is essentially the same sun that shone on the dinosaurs, and will shine on whatever comes after us. Every second, the sun converts about 4 million tons of matter directly into energy, according to Einstein's equation. This matter-energy conversion has continued for 4.5 billion years, consuming a tiny fraction of the sun's total mass. The sun has lost roughly 1/100% of its mass to energy production since formation long ago. Plenty of fuel remains for billions of years of continued operation at current rates of consumption. The energy being released in the core right now is following the same path we traced in detail earlier. New photons are being absorbed and re-emitted, beginning their random walks through the dense plasma of the deep interior. Some are moving outward, some inward, some sideways. The net drift carrying energy away from the core gradually over time. The radiative zone contains energy at all stages of its journey, from just created to nearly escaped. The continuous nature of this process means there is no meaningful batch of solar energy with a definite age anywhere. Energy exists at every depth and every stage of its journey through the solar interior, at all times present. The 100,000-year estimate is an average transit time, not a duration that any specific energy packet experiences directly. Some energy might escape faster, some slower, the average emerging from countless individual random walks combined. The photosphere continuously releases photons that represent energy at the end of its long internal journey outward. These photons escape at the rate energy is produced in the core, maintaining the sun in equilibrium over time. If fusion suddenly stopped, the sun would continue shining for a long time, slowly releasing stored internal energy gradually. But fusion has not stopped and will not stop for billions of years, maintaining the continuous flow of new energy. The solar wind carries particles outward from the sun at speeds much slower than light travels through space. These particles take days to reach Earth rather than 8 minutes, arriving with their own cargo of energy and momentum. The solar wind has blown continuously for billions of years, slowly losing matter from the sun into surrounding space. Yet the mass loss from the solar wind is negligible compared to the mass loss from energy production in fusion. The sun's magnetic field also extends outward into space, shaping the solar wind and affecting conditions throughout the solar system. This field reverses polarity approximately every 11 years, creating the solar cycle of activity variation observed over time. During solar maximum, more sunspots appear, and more solar flares erupt from the sun's surface layers visibly. During solar minimum, the sun is quieter, with fewer visible features on its face as seen from Earth. These surface variations do not significantly affect the core fusion or the photon journey through the interior itself. The core operates independently of surface conditions, its fusion rate determined by temperature and pressure, not surface magnetism. The photons being created now, during this particular phase of the solar cycle, will emerge during some future cycle. The 100,000-year journey spans thousands of solar cycles, making current conditions irrelevant to eventual emergence. The sunlight reaching Earth today was created during a time when the sun looked slightly different than it does now. Core conditions 100,000 years ago were imperceptibly different from today. The fusion rate nearly identical over time. The photons carry no record of exactly when they were created or what surface conditions existed at that time. They are simply packets of energy, identical to photons created yesterday, or photons that will be created tomorrow. This continuous river of energy has flowed from the Sun since its formation 4.5 billion years ago. The first photons to escape from the young Sun began their journeys during the earliest phase of stellar life. Those ancient photons have long since traveled far beyond our solar system, carrying their energy into interstellar space forever. The light leaving the Sun today will similarly travel outward long after our solar system has changed. The future of the Sun is predictable in broad terms, based on our understanding of stellar physics as developed. In about 5 billion years, the core will exhaust its hydrogen and begin fusing helium instead of hydrogen. The Sun will expand into a red giant, its outer layers swelling to perhaps Earth's current orbit around the Sun. Eventually, it will shed its outer layers and leave behind a white dwarf, the spent core cooling for eternity. Throughout the remaining 5 billion years of hydrogen fusion, the process we traced will continue essentially unchanged. Photons will be born in the core, diffuse through the radiative zone, rise through the convective zone to escape. The timescales and conditions will remain similar to what exists today. The Sun, a stable, reliable energy source. Whatever life exists on Earth during this time will be warmed by light from this same ancient continuous process. The photons warming Earth today are not special in any physical sense compared to photons past or future. They are simply the photons that happen to complete their journey at this particular moment in cosmic time now. Photons arriving tomorrow will be identical in every measurable way, indistinguishable from today's photons by any test. The continuous river flows on, each moment's sunlight replacing the last, without any meaningful distinction between them. This continuity provides a kind of stability that underlies all life on Earth and all human activity entirely. The Sun rose today, will rise tomorrow, and will rise for billions of mornings to come without significant change. The energy arriving is the same ancient energy that has always arrived, created by the same process operating continuously. This reliability allows life to flourish, ecosystems to stabilize, and civilizations to plan beyond immediate concerns. The photon journey we have traced is happening right now, has been happening for billions of years, and will continue. New photons are born each second, old photons escape each second, and the Sun shines on without pause or variation. The river of fire flows from core to surface, to space, to Earth, an unending current of ancient energy arriving constantly. This is the nature of our star, the continuous engine that powers our world through photons born in fusion fire. The sunlight that falls on ordinary things each day carries an extraordinary history hidden within its apparent simplicity. The warmth on skin, the brightness through windows, the growth of plants all derive from energy born in nuclear fire long ago. Each photon arriving now began its journey before humans built their first permanent structures anywhere on Earth's surface. The ancient light reaches us constantly, connecting this moment to the deep past through physics alone. The journey of a photon from the Sun's core to Earth spans conditions that challenge human comprehension completely. From 15 million degrees to the cold of space, from crushing density to near-perfect vacuum, from millennia of diffusion to minutes of free flight experienced. The photon traverses these extremes without awareness, simply propagating according to the laws of physics that govern all energy. Yet, our awareness of this journey adds meaning that physics alone cannot provide. Understanding the photon's journey does not change the sunlight itself in any measurable or practical way for us. The warmth feels the same whether we know its origin or not. The brightness illuminates equally regardless of our knowledge. Plants photosynthesize without understanding the source of the light they absorb. Eyes see without comprehending the photons they detect. The physics operates independently of any observer's understanding or appreciation of its workings. Yet something shifts when we know what we are experiencing during a moment of sunlight on our skin. The ordinary becomes a connection to the extraordinary. The familiar becomes a window into the cosmic and ancient. The warmth of afternoon sun carries the heritage of nuclear fusion, of 100,000-year journeys, of stellar physics operating across millennia. Knowledge transforms experience without changing any physical fact about what is happening to us. The sun continues its work regardless of whether anyone on Earth understands or appreciates its nature at all. It burned for billions of years before life emerged to benefit from its energy arriving from above. It will burn for billions of years after our species has run its course, whatever form that eventual end takes. The human understanding of the photon's journey is a brief moment of comprehension in the sun's long existence. This comprehension is itself remarkable, a feature of the universe that has developed only recently on cosmic timescales. For most of the sun's lifetime, no one knew how it produced its energy, or how that energy reached Earth. Only in the last century have we understood nuclear fusion, stellar structure, and the long diffusion of photons outward. We are the first generations to truly know where sunlight comes from, and how it arrives here. The knowledge we have gained connects us to the sun in ways our ancestors could not have imagined possible. We know the temperature of the core, the rate of fusion, the time photons spend diffusing outward through the interior. We know why the sun shines yellow, why it has lasted so long, why it will eventually cease and evolve. This knowledge is a gift of human curiosity and ingenuity, passed down through generations of scientists working patiently. Every beam of sunlight that falls on you has completed a journey of cosmic proportions before arriving at you. The energy was born in fusion reactions before the last ice age, before the first cities, before the first humans. It diffused through the solar interior for 100,000 years, making almost no progress despite traveling at light speed. Then it escaped, crossed space in 8 minutes, and arrived at this moment to warm your skin. The photons that complete their journey tomorrow will be identical in every physical way, carrying the same ancient heritage. The ones that arrived yesterday are gone, their energy absorbed and transformed into other forms in Earth's systems. Each moment of sunlight is both utterly ordinary and profoundly connected to the deep past of our star. The continuous flow ensures that this connection remains unbroken. Day after day, year after year, looking up at the sun, never directly, but aware of its presence above during daylight hours, is to face the source of nearly all energy on Earth. The heat we feel comes from there. The light we see originates there. The food we eat traces back to photosynthesis powered from there. The sun is the origin, the sustainer, the reason Earth is a living world rather than a frozen rock in space. The The photon's journey ends in everything that lives and moves on our planet. The night sky offers a different perspective, showing countless other suns making their own photons through identical processes. Each star is a nuclear furnace, creating and releasing energy that travels across light years to reach our eyes eventually. The universe is filled with these processes, photon journeys happening everywhere. Stars burn throughout the cosmos. Our sun is one among hundreds of billions in our galaxy alone, each doing the same work. The scale of this activity, fusion in countless stars, photons diffusing through countless stellar interiors, is beyond true comprehension. We can state the numbers, but the reality they represent exceeds our intuition developed in everyday human experience. Yet the physics is the same everywhere. The process we traced in our sun occurring throughout the observable universe continuously. Local understanding becomes cosmic understanding through the universality of physical law operating everywhere. The photon's journey ends in many ways, as warmth, as vision, as the energy in food and fuel derived from sunlight. But the end of one photon's journey is part of a continuous flow that never ends while the sun still burns above. New photons are being born right now to replace the ones arriving, the cycle continuing without interruption or pause. The river of energy flows on, ancient and endless, powering our world through the patient work of physics. Tonight, if skies are clear, the stars will appear as points of light, each one a sun, making its own photons. The light from those stars left their surfaces years or centuries or millennia ago, on its journey here to us. The photons were born in their cores even longer ago than that, spending their own ages diffusing outward through stellar material. The night sky is a display of ancient light, each point a connection to distant pasts, beyond counting. And tomorrow the sun will rise again, as it has every morning for billions of years without fail occurring. The photons arriving tomorrow are already on their way, having left the photosphere about 8 minutes before dawn comes. The photons that will leave the photosphere tomorrow morning are nearly at the surface now, completing their 100,000-year journeys. The process continues, reliable and patient, the engine of our solar system operating as it always has. The journey of a photon from the core of the sun to the Earth is complete, and the story we have traced together rests. The core still burns, the photons still diffuse, the light still crosses space, and the Earth still receives its ancient energy. This will continue for 5 billion years, longer than the universe has existed so far, a future we cannot imagine. The sun shines on, and its light reaches us, connecting each moment to the deep past of our star. Good night from the drowsy astronaut.